My name is Reagan Brumage. I'm a Public Services Librarian at the Rakow Research Library, and today is September 16th, 2014. I'm here with Paul Topichak, who has worked in the glass industry for
33 years.
33 years. Thanks, Paul, for joining us.
My
Could
pleasure.
you tell us a little bit about your background, where you came from, and how you got here?
Well, I'm a local product. Corning is my home. My parents owned a small grocery store and bakery, family owned, over on the north side of Corning on Pulteney Street, not too far from here, and which they in turn lost in the flood in 1972. So there's markers indicating that over at the museum, but I kind of lived through that. I was in the first graduating class out of East High School.
Oh, really?
Here in Corning. Before that, there was Painted Post High School, Northside High School, and Corning Free Academy. My senior year, they did all the combining. From there, I went to Clarkson University, where I studied a combination of engineering and industrial management, got my bachelor's degree. And then from there, I went to Penn State University, where I got my master's degree in business. In that time period, I also was a member of both the New York National Guard and the U.S. Army Reserves, where I was an instructor for 6 years. My exposure to the glass industry occurred between my junior and senior year in college, when...
This is at Clarkson?
Yes,
Okay.
at Clarkson, where a neighbor worked at what was then Old A Factory here in Corning, and asked me if I wanted a job for the summer. So it was a great alternative compared to either working in my mom and dad's store or other odd jobs I had, so I was happy to do it.
Yeah, if you said Old A Factory to most people who are, below the age of 20, they might not know what that is. So tell us about Old A Factory.
Old A Factory was where the corporate headquarters building is now. Was actually lined with glass factories. And there were 3 factories there at that time: A, B, and C factory. Eventually, they were combined to form main plant, which, when the manufacturing operation ceased in the mid-1980s, it was main plant that was the last facility that shut down. A factory was, I would call, the heavier manufacturing portion of that manufacturing complex. There were 4 tanks there, including the old hand shop, the hand glass blowing that was used for large bell jars, and similar to what we see over at the hot glass show with the irons and gathering. It was kind of it looked ancient. It was elevated, it was dark, it was noisy. It was actually, I think, quite an honor for the gaffers and assistants to work in that area. The other operations were pressing operations, Pyrex. This goes back to the days of glass baby food jars, glass feeding bottles, baby bottles, and of course the glass coffee pots. There was a lot of experimenting that came out of the laboratory that was then put into production at main plant. In particular, I worked on a couple of glasses. 99 IMG was a Pyroceram glass, which then was being used for building cladding, believe it or not. a glass that was strong enough to withstand hurricane velocity winds, and it never really materialized like Corning had expected.
But they actually produced and sold some
Yeah,
of
it was
these?
it was a rolled sheet glass, and you could roll a pattern onto it. And actually, there were a couple buildings in downtown Corning that had this as a siding or cladding. And one of the attractions to it was you could backlight it,
Oh,
and it created a very beautiful exterior to the building.
I don't suppose those are still there.
Yeah, and then the original counter that cooks, which was another glass ceramic, we melted and formed in main plant.
The stove top.
The stovetop,
Mhm.
yes. And then I was also part of the first, basically melting using the fusion process, which was all the glass melting to that point had basically been horizontal, meaning it was melted horizontally and it was formed horizontally. But the fusion process, which is the process that's currently used to make the LCD glass, was a vertical forming process where the glass actually formed vertically. And I remember one of the amazing things about that process was that it was basically 3 stories deep, if you will. And in main plant, the engineers and construction folks had to dig a pit that was basically below the Chemung River level.
Oh my gosh.
Because the glass needed that height and distance to form itself. Now, the initial application for the fusion forming process and the glass was for auto windshield glass, which Corning had an interest in getting into that market, but that never really worked out. For one thing, I think the auto industry is a tough business to serve. Demand can change quickly, and in some ways, at least then, glass manufacturing processes weren't able to turn on a dime. Startup times were long and costly, and still can be. But anyway, that process ended up eventually going to Harrodsburg, Kentucky, where it was used to make eyewear, clear and photochromic eyewear. And then that same process is what's basically used today to form the LCD glass. The advantage to it was that previously glass of that nature, to get clarity, had to be ground and polished, which was a secondary finishing operation.
Right.
And it added cost and time. And what the fusion process did is it basically made an optically clear or good piece of glass without grinding and polishing. And it did that by using there's a model of it in the museum. It's basically a V-shaped pipe, and the glass would flow from the trough over the sides of the V and then come together, and it got the name fusion because where those two sides, very thin pieces of glass, came together was called the fusion line, and that's where the fusion process got its name. And that's the process that's enhanced many times over, I know, but that's the same process that's used today. Well, that was my introduction to glass making, and for someone in my position, thinking about what was I going to do with my life and career, I was attracted to not only the technology, but the fact that raw materials came in kind of the back end of the plant in rail cars, and then out the front came products that people actually used.
Mm-hmm.
And that fascinated me. So I guess you could say I was hooked.
You were hooked on the glass.
And
that was in the 70s?
that was actually in the 60s.
60s,
That was
okay.
in the late 60s. 66 and 67, and
So they were in working in the fusion, with the fusion
oh yes,
process at that point?
yes,
Hmm.
yeah, that was, well, that's one of the interesting things about Corning the company is that a lot of the glass compositions and a lot of the glass processes have reinvented themselves over the years. They're fascinating processes that have stood the test of time. I worked in a couple of the Corning's ribbon machine plants in Danville, Kentucky, and Wellsboro, Pennsylvania. And this is a machine that was designed in, I believe it was the 1920s, and it's still a state-of-the-art piece of equipment for manufacturing incandescent light bulb blanks. And they were fascinating machines, continuous. They actually looked and sounded a little bit like a locomotive. There were a lot of moving parts. In fact, the operators, the machine made glass envelopes so fast that the operators had to operate it by what they heard, not what they saw, because you really couldn't see the glass being formed.
When you say a glass envelope, what
Well,
do you
these
mean?
would have been, for example, the 75 watt and 100 watt glass light bulb enclosures. Corning made the glass blanks for those, going all the way back to the Thomas Edison days, and this machine was eventually invented by a Corning inventor to economically make these bulb blanks. But what was fascinating about it is that I remember the 7500 watt bulb could be made at a rate of around 20 a second. That's 1,200 a minute. And I know in an 8-hour shift, I was responsible for one of the production operations in Wellsboro. In an 8-hour shift off one machine, we could make about, a good shift would make about 500,000 light bulbs.
Wow.
And a day would be about 1.5 million off one machine. And the furnace at the Wellsboro plant supplied 3 of those machines. And I think it melted about 750,000 pounds of glass a day. And then,
That's staggering.
well, and the bulbs would come off in a random fashion, and then had to be oriented and trayed, because we also put the frosting on the inside of the bulb, and that was done with hydrofluoric acid, a dangerous material to work with. But we had to etch the inside of the bulbs at the same speed the machine was making them.
How?
So,
How did that work?
well, it was all automated traying operations, basically a set of discs and fingers that trayed all the bulbs into, I believe they were 12 by 12 trays, so each tray held 144 bulbs, and it was just continuously flowing over a shot tub that then squirted. It was 30% hydrofluoric acid to the inside of the bulb, and actually the hydrofluoric acid would eat the inside of the bulb and give it that frosted appearance, but made it very fragile, because the acid would actually create, if you looked at it under a microscope, a kind of a jagged appearance on the inside of the bulb. So then it had to go through what was called a fortifying process, which was actually a healing process to the inside of the bulb, which used a weaker concentration of hydrofluoric acid, about 10%, to heal it. And this was all being done at that speed. And these would be bulk packed, and then we would ship them to companies like Sylvania and Westinghouse or Philips. And we made a lot of different kinds of bulbs. I remember the tail light bulb, I believe it was called the S8W1C, for your automobile tail light. It's a much smaller bulb, and that used a double cavity mold and could be made at a rate of about 2,000 a minute. And even then, automation was coming of age. We actually This would have been in the mid-'70s when I was in that plant. And we were operating that line with basically 3 people.
I was just going to ask you, what kind of staff do you have for that, and what are their jobs?
Well, there was a machine operator, and then we basically had a quality inspector, and then a person who was operating an automated bulk packing system. Now that would be just for plain bulbs. The frosting line definitely had a lot more people involved with it to tend to the equipment. And then when we made things like, the old TV and radio tube bulbs and so on, those had to be cell packed and required a lot more inspector packers to package those. But the high-speed volume lines were actually quite efficient. I don't know if cost is an appropriate thing to talk about here or not, but I remember that we sold these at, and I just remember it because these are figures that are easy to remember. We sold them for about $10 a 1,000.
Wow.
So we were making these for about a penny a piece.
Mm-hmm.
And that's pretty amazing when you
Yeah,
think
it
about
is.
it. But it's one of the ways that lighting, again, one of those things made out of glass that we kind of take for granted, became so affordable. People will ask sometimes, even during the tour, about Corning's role in the finished bulb business. And Corning never made finished bulbs, only the glass enclosures. In fact, I'm quite sure that Corning was legislated against legally through antitrust to go into the finished bulb business. Eventually that would have expired, but by then the distribution system for getting bulbs into all the family grocery stores like my mom and dad had and so on was set up by companies like Westinghouse and Sylvania, and it was a little late for Corning to get into that part of the business, but they continued to make the bulbs, and eventually as European glass makers wanted to make their own bulbs, Corning built and transferred ribbon machines to countries like Hungary and Romania and Russia, along with glass plants. That was a very important aspect of Corning's international division, was marketing, selling
The ribbon machine?
technologies like that.
Where were those machines made?
Well, actually, some of them were made in the plants where the ribbon machines existed. I know Wellsboro, Pennsylvania, made several ribbon machines for export. That's where the technology resided. That's where the ribbon machine mechanics were, who knew and understood the machine. The electricians to wire it with the instrumentation, the folks who had worked with those processes for years.
So do those machines have the melting capability built in also, or does that happen and then it moves into the machine to be put into the molds?
No, the melting process was separate.
Okay.
It was a glass melting furnace, a large one. And essentially the glass flowed out of the furnace through an orifice in a continuous stream. And I mean, if you looked at it, it would just be almost an orange, white, hot stream of glass coming out of the orifice, and then it flowed onto a set of plates that had an opening in it, and it's through that opening that the initial gob of glass began to form through gravity. And then there were a set of molds on the bottom that were going in a different direction. And then there were a set of blow tubes on top that would come down and engage that orifice plate where the hole is. And then that's where the puff of air would be injected. And then the molds would come from the bottom and grab that elongated gob and then spin. And the bulb was actually formed on on a cushion of steam. The molds were coated in a cork-like substance that would absorb water, and you have to remember this is all going at that rate of 1,200 a minute, and it's all synchronized. The molds coming one way, the plate on top with the gob being formed, and then the blowpipe from above coming down, and it's all being synchronized. And then when the molds disengaged, they would be cooled with compressed air and then sprayed with water, and then the process would start all over again. But this is all going at a speed that you really you couldn't see. It was moving so quickly. It was fascinating. And what was interesting was that I mentioned that the operators operated the machine by what they heard, not so much what they saw.
Mm-hmm.
Then in the 70s, OSHA and the Environmental Protection Agency came of age, and so all of a sudden, areas where hearing protection hadn't been required or even thought about, for that matter,
Right.
now became mandatory. This really led to the advent of a lot of technology to operate these machines, because now the operators who, in fact, I remember when the requirement was that hearing protection had to be worn, the noise level in the plants was such that it required double hearing protection, earplugs and ear muffs. The decibel level was so high, and this was just because of the use of compressed air and just the noise associated with the running of the machine. But it led to the advent of a lot of optical pyrometry, ways to sense temperature of glass and molds using optics, and readouts then in these soundproof rooms where the operators could now
So just moving them back from the...
yeah, getting them out of the noise, basically. But for them, it was a huge transition. I mean, those operators had grown up learning how to run the machine that way. I remember on the frosting lines where we used the hydrofluoric acid, and that was an area that I was responsible for. We had frost operators that used to check the intensity of the shot tubs where the hydrofluoric acid was by placing a little drop in their hand and seeing how long it took it so they could start to see feel the burning sensation. That's how they checked whether it was strong enough, because over time, injecting the acid into the bulbs and creating fine bits of sand, it would dilute the intensity, and you had to kind of replenish it. And you think about that today and think, my goodness, and but then, and this wasn't that long ago, it was hard to break them of that habit, because that's what they had been used to. That's how they learned how to operate the equipment. But over time, and with a lot of training and coaxing, and as the new generation came along, it was a lot easier to enforce those required safety standards. But that was a big transition when all that occurred. That actually is what led to a lot of changes in Corning's glass melting technology as well. Whereas older furnaces used a lot of combustion air and natural gas, and all that would kind of ignite in the melting area of the furnace itself. Corning came up with zonal and Vermel melting processes, which was a technological answer to the pollution requirements that occurred. The smoke and the plume that we used to see. You look at the old pictures of where the corporate headquarters building is now. You see the stacks, and I can remember growing up in Corning, there were plumes of of smoke all the time. And really what that is it's particulate. And it's the products of combustion. And when ingredients like sand and alumina and boron and so on melt, they give off an effluent or a product of combustion that basically is microscopic particulate that goes out as a plume or a smoke. Of course, that then deposits everywhere, and that's one of the issues with you know, that type of manufacturing. But you know, nobody knew any better.
Right.
And but as time occurred, you could use things like scrubbers or electrostatic precipitators on those stacks or chimneys to clean the smoke, if you will. That was
particulate.
The particulate, and that was one way to deal with it. Corning, though, always a great technology company, came up with new melting processes to deal with it. Putting those devices on the stacks was expensive. It was an added cost, and they were also expensive to maintain, and it didn't really eliminate the problem. It did as far as a plume went, but you were still dealing with a particulate. But the melting process is basically, kind of in a nutshell, going to a lot of electric melting as opposed to gas and air, and using the unmelted batch blanket as an insulator, and it kept all the products of combustion contained in the glass bath. And the Vermel process was a vertical melting process like that, with basically unmelted batch in on top, electrodes on the side of the melter, and then the glass would melt as it progressed on down through that cylinder, which is how the pressware makes the Corel glass. They're now, of course, part of World Kitchen, but that was an innovation that...
So they're still using the Vermel?
Still using Vermel, and that stands for vertical melting. Everything, and the melting process was now vertical instead of horizontal. Horizontally, originally the batch would flow in the first section of the furnace, and then it would go to the second section and then to the refining end, and all the time it's being melted and cured. And that actually might take, could take a couple of days actually for a batch to enter in the melt end and make it out the front end. Of course, that was happening continuously, but the throughput time could easily be a couple of days. So the Vermel process was one, and the second one, now I never worked with the Vermel process, but I mean, I'm familiar with what the technology is, but I did work with the zonal process. And the zonal process basically used the same horizontal melting, and it had a melt 1 and a melt 2 and a refiner. And basically, raw batch was fed in the back end of the furnace through what was called a blanket feeding device, kind of almost a long trough-like that was constantly feeding batch into the back end. And you could look into the back of the furnace, and what you saw was unmelted batch. And all the heating was done underneath using, we used 2-inch molybdenum electrodes that were, in some cases, 4 feet long. These were
big electrodes.
These were big electrodes, 2 inches, 4 feet long, and a tremendous amount of electrical power going in there. And that's how the melting was done. It created a lot of challenges because that amount of electricity going into a glass bath, and of course the batch becomes molten, so it conducts the current. It created a lot of convection currents, and that has a lot to do with how glass melts. So it was a whole new technology, again, for people who were used to melting glass the old way. These were very, very innovative processes that took a little time, but eventually were mastered very well. Occasionally accidents occurred. With that amount of electricity, if anything metallic got in the furnace, and we used a lot of metal separators to make sure that in the batch handling process, because remember we're unloading rail cars and we're dealing with conveying systems that have a lot of metallic parts. But if anything metallic got in the furnace, it would melt and it would work its way down into the cracks and crevices of the refractory block that was the lining for the furnace. And then electricity is going to follow the path of least resistance, and the molten metal would be that path, and that's where all the current would go. And unfortunately, I experienced a couple of situations where basically the bottom of the furnace ruptured, and I remember that happening one time, and I was actually in the front end of the plant, and the noise was so loud it sounded like a shotgun blast. And then we have molten glass running out the bottom of the furnace, and about the only way you can stop that is, and this our emergency response teams and the local fire departments were trained to do this, is you kind of have to let it pile up from the cave or the basement area, putting water on it all the time, and you let it cone up, and eventually it would work its way up to where that hole was, and it would plug itself. And that's how we stopped the glass from, I mean, a good share of it would have emptied out by then.
How high would that cone be?
Well, the basement was a full story.
Oh my goodness.
So yeah, you'd have to let it cone up basically
Through that.
1-story level, to at least, and those basements were higher ceiling, probably 10, 12, 15 feet.
Were there a lot of people around, or it would have been fairly isolated?
No, when something like that happened, a lot of people had to show up and get fire hoses out and
Spray the water.
contain it. I remember, this was amazing too, and Corning stopped doing this, but molybdenum was considered a precious metal, like rhodium or platinum. And we used a lot of those materials in the furnaces in other ways, but every few years we would have to rebuild the furnaces. And because molybdenum, or I'll call it moly, was viewed as a material worth saving, we actually invented a process to pull those electrodes hot. You had to get them out hot, because if you left the moly in the furnace and then drain the furnace to cool it down and repair it, the moly at that temperature, when it's exposed to air, will crystallize and disintegrate. So at that temperature, it has to kind of always be covered in glass. So we would have to pull those electrodes while the furnace was still hot. And it came up with a device, almost a jack-like device, and you'd superheat the bottom and then pull this. And these 4-foot rods would come out white hot, and then they would be put immediately into a trough, if you will, of a sand-like material. It was called supersil, and it would cool down slowly, and we could then recover the moly. But what was interesting about the whole process is that when that moly rod came out, right behind it was the molten glass. So the team that did this had what was called a water-cooled plug, and it was a plug that was actually kind of in the shape of a pyramid of sorts that was water-cooled. And when that electrode came out, then you had to jam that plug up into that hole by hand.
Oh my goodness.
And hold it there until that water-cooled plug froze that electrode holes solid.
That must have been a hot job.
Very hot, very dangerous, hard
Yeah.
to train people for. And I remember we were training a group. We were doing this in Parkersburg, West Virginia at the time, where that technique kind of evolved. And we were training another group of people in doing it. And underneath a furnace like that, there's not a lot of space anyway. it's hot, and there's a metal catwalk, and you've got a lot of people down there. I remember the first time one of those came out when this other group was there, and a few of them just ran. It was terrifying to see that come out. Well, I think over the years it was decided that the risk wasn't worth the reward, and that recovery process for the moly was eventually abandoned, as far as I know.
Mm-hmm.
But again, it just speaks to this whole, I think, idea that glass making is complex.
It is.
It's dangerous, and I know the index presses that made, like the consumer ware, pipe plates, utility dishes, and so on. They were indexing at a rate of about 1 a second, and because it was, when you have a whole table full of molds, temperature is really key in forming glass, and if you have to shut that down for any reason, things get a chance to cool off, it's a long startup process to get it back where it should be. So when molds had to be changed because they, or a plunger, which actually was the device that came down from the top and actually did the pressing, the operators would do that on the fly while the machine was still running and indexing.
Even with the ribbon machine? And
No, not the ribbon machine.
Okay.
These are index pressing machines.
Let me show you a picture and see if this is similar to what you were
Okay.
talking about. This was a picture that came from the Pennsylvania plant.
Wellsboro?
No, Charleroi.
Charleroi.
Yeah.
I worked in Charleroi. Yeah, exactly. Yeah, that's the table of molds that I was referring to.
Okay.
Okay, and a glass gob would be dropped into those molds, and then there would be a plunger that would come down from above and basically press that glass out the sides to the desired shape. Okay, and it was these molds that if they got a burr in them or any kind of a defect that would have to be changed. And of course they're bolted onto the press, and so the operators would change those on the fly while the press was operating. Yeah, good old Charleroi.
It's sort of like a pit crew kind of.
Well, yeah, very much. And here again, a lot of compressed air was used on these processes, and but essentially the process is the same. And again, the rate at which these molds lost temperature had a lot to do with the finishing and eventual annealing of the glass. So it looks maybe a little rustic, but actually there's still a lot of science involved in controlling the speed and the temperatures properly so the glass doesn't break.
Is he just doing checks, or what do you think that worker is doing there?
Well, I'll tell you what he's doing there. Of course, this was automated out, but if you look closely, he's got a set, probably back then these were asbestos gloves, and he's actually taking the piece out of the mold.
Mm-hmm.
Can you see that?
Oh, I do see that.
See here, they're in the mold, and here he's actually lifting it out, would have put it on a, we called it a Lear belt, but that's the annealing process. All glass has to be annealed. If you allow it to cool naturally, it's gonna break. The thinner sections will cool quicker than the thicker sections. The outer area will cool quicker than the inner area. It'll set up stresses and it'll break. So these pieces, along with most glass, have to go through an annealing process where it's all reheated almost to the softening point, which would be around 900 degrees, and then cooled slowly so everything cools at the same rate.
Mm-hmm.
So he would have been taking it out of the mold and then putting it onto one of those Lear or conveying belts, which basically the Lears were, that was L-E-H-R, and they were basically, the best way to describe them is they're long ovens.
Mm-hmm.
which brought the temperature back up and then brought it down at a slow rate so everything cooled at the same rate.
And so they're making the pressware.
That looks like a pie plate.
Right.
But
And
they made the meatloaf dishes, the large utility dishes, which are still sold.
mm-hmm.
And those initially were made out of Pyrex glass, which was a borosilicate glass. That's a glass that has boron in it,
Mm-hmm.
in the form of boric acid or boric oxide. And that Pyrex, the borosilicate Pyrex, got its strength from the fact that glass had a lower coefficient of expansion. It's the same glass that is used in the scientific glassware industry. You might recall from your chemistry class
Mm-hmm.
that you could take a Pyrex beaker or flask, put it on a Bunsen burner,
Right.
heat the bottom of it,
Direct heat.
and then set it on a cold or even wet laboratory top, and it wouldn't break.
Mm-hmm.
And it wouldn't break because it has a low coefficient of expansion. Window glass or soda lime glass has a coefficient of expansion of around 90, and here we're talking about infinitesimal movement of molecules is what that's really measuring. But borosilicate glass had a coefficient of expansion of about 32. So you could say that window glass had 3 times the expansion capability, and probably actually exponentially more than that. But by measurement, 3 times what borosilicate did. But that was an expensive glass to melt. It melted at a much higher temperature, several hundred degrees higher than, say, soda lime window drinking glass. And eventually, and Charleroi still does this. That plant is still in operation as part of World Kitchen. Perfected the air tempering technique, which allowed the use of the less expensive soda lime glass. And then it got its strength from essentially a combination of heat and air tempering, which created stress in the glass. Stress is normally bad.
Right.
But if you can do it in an organized way, it can actually create a lot of strength. And it did that by putting the surface of the glass in compression, or a pushing strength or action of the molecules. But for every area of compression, there is an area of tension. So while the surface was in compression, and it got in compression by blasts of cold air that were hitting it when it was hot, the interior of that would have a lot of tension. That made the product very strong as long as you didn't break it, or a sharp instrument didn't penetrate that initial compressive layer. But most of the Pyrex that's still sold today is the tempered soda lime, as opposed to the higher expansion tempered soda lime, as opposed to the lower expansion borosilicate glass. So, yeah,
And I
interesting.
know we've been asked before at the museum and the library about, borosilicate and soda lime and tempered, and then there's a whole other category like the Pyroceram that also came out for the consumer products. Did you ever work with those?
In a way. I never worked in a Pyroceram plant, but in main plant made Pyroceram, and we had a Pyroceram-like material that we used to make the Corel cup, actually, in Charleroi. But, I mean, the best way I would explain that from my knowledge of it is that glass is, in its normal form, is an amorphous solid, meaning it has the characteristics of a solid, but it has the random molecular structure of a liquid. It's why it flows.
Mm-hmm.
Solids have a very uniform molecular structure. It's very organized. And glass can be converted to a glass ceramic, which then basically becomes a crystalline form of glass, and it basically becomes a solid by growing crystals. And that's done, the Pyroceram glass, because the ingredients in it has what's called nucleating agents. And if you put the glass through a heat treating process and hold it at a certain temperature long enough, it will grow crystals. And the structure of the glass changes then, basically from an amorphous solid to a solid. And it becomes crystalline as opposed to non-crystalline, which regular glass is non-crystalline. And so the Pyroceram, which would be the Corningware, the Visions cookware,
which is see-through. How is that? Because
well, if it's basically a phase of that heat treating process. In the museum, that tower that you see in the Innovation Center basically shows the transition from a semi-clear to a white. The white is caused by, I think it's a process, if I remember right, it's called vitrification, which is, again, the forming of those crystals that will turn it white. A process, by the way, that was discovered by accident. I think one of the scientists left a piece in a kiln or a furnace too long. He thought it'd be melted, and when he came back, he had this white crystalline structure. Corning actually at one time, this was back in the old main plant days, or A factory days, made missile nose cones out of that same material. The Nike Redman missile nose cones were made of a Pyroceram material. I always found it interesting, and that, you know, the household use of that type of glass for cookware, it was indestructible. I mean, people that had that pretty well had it for life. In fact, I remember a commercial with Visions cookware where they actually heated the bottom of the pan with a blowtorch until it got glowing red, and then just dumped it into a bucket of ice water, and to show that it basically was indestructible. Well, that same glass was used for the Department of Defense for those nose cones, and one of the other interesting advantages to glass is that it's essentially unaffected by or impervious to electrical interference. So when you think about a missile nose cone and the guidance system that would be in it, you wouldn't want a lightning storm in the atmosphere to cause anything to go wrong with that. And you certainly wouldn't want the enemy to be able to jam it. And because the Pyroceram and glass in general is a good insulator, prevented all that. That was a great application for it. So all the way from the Department of Defense to the kitchen, basically, using the same glass.
yeah, well, I've heard Corning is kind of famous for repurposing different types of materials and different processes. What have you experienced with how they have worked with technology and R&D and?
You know, well, Corning, once Corning got into the commercial and industrial application of glassware, it has established itself as a world-renowned innovator. And it's interesting in that a lot of the glass compositions, and to a certain extent maybe even some of the glass forming processes, continue to find new applications. It's like the fusion process that we talked about earlier, that was initially invented to make auto windshield glasses, and now makes the LCD glass for flat panel TVs and PC displays and so on. the ability to color glass, taking the typical forming process and finding a way to introduce metal oxide colorants at the through color cell technology. Prior to that, if you wanted to make a glass of a particular color, you had to change the whole glass bath. And so you had a whole tank full of glass of that color. With the addition of color cell technology, it allowed you to take one forming position and introduce the color in what was called the foreharther, which was the discharge to the actual pressing operation, and add the colorant there.
When was that?
Color cell technology came about in the, we used the first color cells in Charleroi, and that would have been in, let's see, the mid-90s maybe? I was there from 1989 to 1999. And
In Charleroi.
in Charleroi, yeah.
And what were the products that you were working with there?
Well, Charleroi, again, was basically consumer products.
Consumer products. So that was all they did?
That, and they made the, at that time, we made the cup for Corel.
Oh, okay.
And it was a little different glass. And prior to that, I was in Parkersburg, which made scientific labware out of borosilicate glass.
And that was through pressing, or is that hand?
That was, well, that was a different forming technique. That was called Vello tubing, V-E-L-L-O.
I've
Vello.
heard that term, but I couldn't
Well,
tell you what
Vello
it
tube
means.
draws, another fascinating process. I mean, we had the ribbon machine, which we talked about, which was a continuous stream of glass. The pressing operations basically used gobs of glass, which were cut, dropped into the molds, and then formed. Vello tubing was a continuous flowing process, and it used, this is what they were called, and it's pretty much like it sounds, used a ring and a bell technique to form the glass. If you could envision an orifice like a donut, that would have been the ring. And the bell was much like it sounds. It was a bell-shaped or triangular-shaped, for the most part, piece of metal, usually either high-quality steel or maybe coated with platinum. And that bell would sit in the center of that orifice, and then by raising and lowering it, you controlled the flow and thereby controlled the outside diameter of the tubing. And the glass would flow between the ring and the bell.
Okay.
And then air would come down through the center of the bell, and then you'd end up with a piece of tubing that would be continuous flowing and would transition from the orifice onto a set of usually graphite type rollers where it would travel maybe for several hundred feet while it was cooling, and then would be cut off. And that's how tubing, fluorescent light bulb tubes are made. Tubing for laboratory and scientific glassware like culture tubes, pipettes for titrations, tubing that was used for ampules and vials and syringes. Again, the borosilicate glass, that was borosilicate glass, was desirable because it was much more stable than soda lime glass, and you didn't have to worry about anything leaching out of the glass. With soda lime glass, if it's exposed to weather conditions, temperature and humidity long enough, it'll go through a process called weathering, where the soda will actually come out of the glass a little bit. Sometimes if you use a drinking glass long enough, you'll see that it gets a little cloudy. That's kind of the effect that weathering does, but borosilicate glass won't do that. And when you're dealing with the medical industry, scientific products, especially where you know, medicines or blood samples are involved, you don't want anything leaching into it because it's going to contaminate the results. So borosilicate tubing was preferred for that. So we sold that glass to companies like Fisher Scientific, Becton Dickinson, Wheaton Industries, who made vials and ampules and things like that out of that glass. And in fact, one of those borosilicate glasses was called a neutral borosilicate glass. And we added to the batch barium oxide, which kept the pH or the acidity of the glass neutral, which was another advantage to glass vessels, if you will, syringes, culture tubes, or whatever that were, you know, containing samples, blood samples, or whatever it may be, medicines, serums. Not only was the glass very stable, but we also had a glass that made the pH neutral, so that just another advantage to that industry.
Mm-hmm.
So yeah, that was all that was in Parkersburg. The ribbon machine plants I worked in were Wellsboro and Danville, Kentucky, which Danville also made lead glass tubing before your time, but you maybe remember seeing the old photo flash camera film that had the post and the thing, and then it had a big bulb in it.
Mm-hmm.
Well, that was lead tubing, and we made the tubing for that and sold that to companies like Sylvania, who actually made the flash bulb. And lead tubing also was used for the exhaust tubing for incandescent bulb manufacturing. The bulb manufacturers had to pull a vacuum on the bulb to make the finished bulb, and so they had to have a tubing to exhaust the air. And that lead tubing was desirable because it was softer and had a lower melting point, and could be used in conjunction with the bulb making process. That was interesting too, because lead tubing got lead in it. Lead is a dangerous material to work with, and you know, much like lead crystal was. But yeah, those were fascinating processes. I remember the exhaust tubing. Those they were called draws, and again, that tubing would come through that Vello forming process, through that ring and bell orifice situation, and be turned. But exhaust tubing was about the diameter of a pencil, and when that tubing was cut, it was basically chopped. And there was a high-speed wheel that would come around with a chopping blade and chop it, and the speed of that draw was around 35 or 40 miles an hour. And those individual pieces of glass that were at that point were about 4 feet long basically went airborne.
Right.
And they were controlled on a slanted stellite table until they slowed down enough, and then they hit a bumper on the end and fell onto the conveyor and would be packed.
How long was that table?
Well, it could be that fanning table could be, I'm recalling now, maybe 30 feet, 40 feet, and then it would hit that bumper and drop. But occasionally, that whole cutting process could get away from us, and when it did, those arrows of glass would go everywhere.
Oh my goodness.
And I remember seeing we had some corrugated roofing, and I remember seeing that glass actually sticking in pieces of corrugated metal. And again, just another indication of some of the dangers associated with those kind of processes. But what was amazing is You know, I learned there, kind of a lesson in life almost, that dangerous jobs can be done safely. And that's the whole key to it, is you know, you just working around temperatures and having to change things while hot glass is melting. We used to have in the delivery system, which was called a four-hearth, there were stirrer chambers which homogenized the glass to make sure there weren't any impurities in it. And occasionally those stirrers would fail, and they would actually drop into the molten glass. Well, you had to get them out of there. And there's no easy way to do that. You know, you have to get up on the forehearth and uncover it and basically get it down in there with tools, forceps.
What wouldn't melt?
Forceps.
Oh, steel or...
Water-cooled forceps, and fish that out of there. And I remember one time that operation was going on, and we had an inspector in the plant. And I don't remember if it was a Corning inspector or an ocean inspector, but anyway, the people were up there, our mechanics were up there dressed in their fire-resistant suits and so on, but they didn't have safety glasses on. And someone commented, and I said, well, there's a reason they don't have safety glasses on. I said, because they would melt. And they would have. They would have melted. And so, yeah, the lesson in life was that, you know, when you're working with those kind of processes, that even though they are inherently dangerous, some of the ingredients, some of the processes, some of the temperatures, some of the speeds, they can be done safely. And so through training and proper procedures, that's what we tried to do. And we actually, for the most part, had admirable safety records in those plants, because it was something that we really paid attention to, because if you didn't, it could be life-changing or life-ending.
Right.
Yeah, it was just that element of danger.
I have heard some stories.
Yeah. Yeah. So, yeah, it was, well, it was, as I said at the beginning, I got hooked on glass making, and I was fortunate to have worked in plants in 4 different divisions: lighting products, technical products, science products, and consumer products. And they all used different glass compositions, and they all used different glass forming techniques, and different glass melting operations. So for me, in my time, there was never a dull moment. The plants operated 24 hours a day, 365 days a year, and never shut down. And a problem could occur anytime. The processors didn't know what time of the day or night it was. And so whether it be on off shifts or weekends, you know, the coverage, the skill levels had to be there to do whatever troubleshooting was needed. We only shut our furnaces down if for some reason volume or orders were such that we couldn't support running it, which was very infrequent, because it was very time consuming and expensive to bring a furnace back up from a cold state. The only other time we shut them down was to have them repaired and rebuilt. And depending on the type of glass and the amount of throughput through the furnace, that would be once every few years, maybe 2 to 3, depending on the type of glass, or maybe as long as 5 or 6 or 7 years, depending on the throughput. And, some glasses were much more corrosive to the refractories that were used to line the furnaces than others. So it was nonstop. You know, that there was always action. You know, now that I'm even retired for a while, I still miss the action.
You miss the action.
There's parts of it I don't miss, but you know, I miss the action. There was just something always going on. New innovations and products which pushed the process capabilities, and new technologies, ways to make the product more efficiently or less costly. And I mean, we always welcomed that because it was, you know, that was the nature of continuous improvement. It's how we kept costs under control. And a lot of those old operations that I've spoken to you about are, you know, Corning doesn't do those anymore. We're out of those businesses. But those are the businesses that funded the research and development that led to what we have
But
today.
some of those processes are still being used elsewhere, right?
They are. Yeah, it's not like they went away.
Right.
You know, Corning, as rightfully so, you know, reinventing itself. Those were very high fixed cost operations. I always likened I know we did a lot of communicating with our employees, all payrolls, union and management, and you know, the need to continually cost reduce and improve productivity. Not something that everyone wanted to see because it meant jobs changed. In some cases, jobs went away.
Mm-hmm.
But I used to liken our cost structure to a kettle of water on a stove. It takes a certain amount of heat to bring it to boil. But then you can't turn it off. If you want to keep it boiling, you've got to keep a certain amount of heat always applied. That's the same way with the glass furnaces. And it really didn't matter how busy you were or how much volume you had or demand. If you wanted to keep the glass hot and available, you had to keep a lot of energy going in there.
Mm-hmm.
And that's why those were such high fixed cost operations. It could, well, I remember I mean, it would take a week or 10 days to heat a furnace up from cold state. But yeah, so, you know, the challenges were always there for productivity and cost improvement, but it was a great environment. You know, Corning was a great company to work for. Demanded a lot, but very good in return in terms of taking care of their people. Likewise, the union employees, I think, had a respect for Corning. It was a paternalistic type of company. In most cases, these plant locations that I spoke to, Wellsboro, Danville, Kentucky, Parkersburg, even the city of Corning here, relatively small towns.
Mm-hmm.
So Corning was always a major employer and always a good corporate citizen and well respected, and that meant a lot too. You know, so the work was interesting, and working for a good company was great, and it was a challenging and interesting
And you
30
got
years
an
for me.
encyclopedic tour of all the glass forming processes, and I don't think I've talked to anyone during these oral histories who's worked with as many different types of glass and processing, and that's interesting. I think Kelly has some questions.
So I just had a few other questions, kind of Pyrex specific. So,
okay.
did you work much with Pyrex, like with your job, like with your role and with your job? Was that specifically for that brand, or were you working kind of across the board with different types of?
No,
printing
the
products?
plants generally supported a number of businesses.
Mm-hmm.
When I worked for consumer products, Pyrex would have been one of the brands.
Okay.
Corel would have been another one. Revere Cookware would have been another one.
Okay.
So,
Okay.
yes.
So had an umbrella.
A
of all the-
variety.
Yeah.
Mhm.
Okay. And then with your job, what was your position like?
Oh, what did I do?
Yeah.
Well,
and you've been talking a lot about it, but I'm
yeah,
just
well,
curious about the specifics.
okay.
Sounds like you were an engineer by training.
Yeah, I kind of started in that role. When I went to work full time for Corning, I started as a process engineer, and then I worked as a shift foreman out on the production line, and then I worked as a quality engineer,
Okay.
and then from there I basically went up the production chairs to department head,
Mm-hmm.
production department head. I was an engineering department head,
Okay.
and then production superintendent and plant manager.
Okay.
I managed the plants in Parkersburg and Charleroi, and then finished my career in procurement, basically, when we began sourcing products.
Mm-hmm.
And actually, during that time period, I was part of the consumer products company then, which had been sold to become World Kitchen. And Corning had bought Revere Cookware.
Okay.
And we moved that operation from Clinton, Illinois to Surabaya, Indonesia.
Oh wow.
And that's how I ended.
Okay.
And so, yeah,
Great.
a variety of engineering and production and manufacturing positions.
So I have a pretty specific question about patterned Pyrex, like the opalware. Oh, two questions. With that opalware, is it like, how is that composition different or better than the borosilicate or aluminosilicate or any of the other types of glass that were being produced?
Well, Charleroi made a lot of the opalware.
Mm-hmm.
Unfortunately, that operation had shut down by the time I got there. But it's basically a soda lime glass, but it had an opalizing agent in it that gave it that milky
Okay.
white appearance. And
So it's tempered soda lime because you can put it in the ovens.
yes,
Okay.
yes, yeah.
Okay.
And it was heat treated and tempered, yeah.
Okay. That's helpful. And then the patterns that they put on, is that a fired on process? Is it similar to how they put patterns on Corel? Because I've been to the World Kitchen factory and seen that they have kind of a silk screening process, but then they do fire on this type of enamel. Is that
Yeah,
similar?
a couple different ways that can happen. Decals can be used that are
Mhm.
placed on and then fired in,
Mhm.
or silk screened and decorated and fired in.
Okay.
And that was another change. A lot of those colors used lead in
Mhm.
the pigments, and it was quite a transition going from lead to non-lead.
Hmm.
And but yeah, decals or silk screening.
Okay. Great. And you said that the opalware stopped being produced when you were there. So was it in the-
Before I got there?
Was it? Okay.
I think that would have been. I was there from '89 to '99, and I think
Oh, okay.
it shut down in
Yeah, I
the
was thinking the 80s, I think.
'80s,
wasn't it?
early '80s.
Okay. Yeah.
A good product and still popular at yard sales, garage
Right.
sales, and
How do you feel about Pyrex?
yeah. Well, a lot of the military mugs were made out of
Yeah.
opalware.
Mhm.
They say that in World War II in particular, veterans will say they don't know how many millions of those cups are
Right.
probably at the bottom of the ocean, because
Yeah.
they used to toss them over to shoot at them.
Yeah.
Target practice.
That's funny. So, and with the stuff that was used for the military, was that also the tempered soda lime that you, so kind of the precursor for the opalware that was produced for the market? Do you know? I know it's pretty early.
Well, the military,
Question.
the only military application that I'm aware of was the Pyroceram for the missile nose cones. Is that what you're referring to?
No, they had some messware. We have some messware.
Oh,
like-
the messware.
Yeah, yeah.
Yeah, that would have been, that was opal messware.
Okay.
Yeah, that was opal
Yeah.
messware.
It was a little thicker, I think,
Yeah,
than
thicker,
the
right.
stuff that was produced later. But
And that milky white color.
Yeah.
Yeah, definitely. Yeah,
okay,
yeah.
cool. All right. Will you be available for questions later? I know we're finished, but if we
Okay.
have questions about any specifics.
Sure.
Okay. Great.
Yeah, if there's, I mean, I didn't make anything up, so whatever is in there is what I
I know you
remember.
did.